welcome back to our channel. Today we're going to take a ride, but not just through space, but through time itself. So sit back, open your mind, and let's embark on a journey across the very fabric of the universe. We begin nowhere and everywhere. Intergalactic space. Billions upon billions of kilometers from Earth, a silent void between two giants. The Milky Way, our galactic home, and Andromeda, another majestic galaxy, spinning with hundreds of billions of stars. Out here, space seems empty, cold, black, infinite. But look closer. We're not suspended in nothingness. We are surrounded by something far stranger. An invisible, cosmic web. The grid of spacetime itself. This grid isn't made of wires or strings, it's imaginary, yet fundamental. It bends, stretches, and ripples. It defines how everything moves, from stars and planets to light and time. Here the grid appears calm. Still, throw a marble and it floats away forever through a motionless sea. But that stillness is an illusion. Fast forward time and the grid flows ever so slowly like a vast river. It carries stars, gas clouds, and even dark matter, pulling everything in its path. And look closely, the Milky Way and Andromeda are inching toward each other, silently, inevitably. In a few billion years, they'll collide and merge, birthing a new galaxy, long after we're gone. But wait, if these two galaxies are coming together, why do we say the universe is expanding? Because it is. A century ago, scientists discovered something shocking. Most galaxies are actually moving away from each other. The universe is stretching. Like a balloon being inflated, the grid swells, dragging galaxies apart. And as they flee, their light stretches too, turning red. This redshift is proof that the expansion of the universe is not slowing down. It's speeding up. Pushed by a mysterious force we call dark energy. Let's rewind to the beginning. 13.8 billion years ago. The entire universe was compressed into a single, unimaginably hot point, a quantum soup. Then, in a blink, it exploded outward. Space itself inflated. Time began. The Big Bang. What came before? No one knows. But out of that chaos, tiny fluctuations grew. They attracted matter, which clumped into webs, filaments, halos, and galaxies. Eventually, one small planet formed. Earth. Today, we orbit a star. The Sun. Just one of countless others. Its mass curves spacetime, pulling the cosmic grid inward like water spiraling into a drain. This is why planets orbit. They move forward, but the flow of spacetime pulls them inward, keeping them from drifting off. Even this Earth curves spacetime, just enough to hold the odd moon masking our satellites and the International Space Station in orbit. Objects don't orbit because of invisible strings. They orbit because they're surfing the curves in space. And deeper down, the grid flows faster, near the surface of the Earth. Escaping that pull takes enormous speed. That's why Wasoyawakis say, rockets must burn so hot. Drop a few apples? Spacetime pulls them down together and stretches them apart. This distortion has a name. Tidal forces. It's the same force the moon uses to stir our oceans, and even Earth's rotation. Slightly to drag spacetime one with it, affecting how falling objects twist and turn. Go deeper. Inside the Earth, pressure builds, holding the planet from collapsing under its own gravity. At the Jadaninvri center, a marble would sit perfectly still, cradled by equal forces in every direction. Jump through the Earth, if you could survive the heat and pressure, and you'd emerge on the other side in mere minutes. But nothing lasts forever. In about 5 billion years, the sun will run out of fuel. Its core will collapse into a white dwarf. As the outer layers drift into space, a ghostly, planetary nebula. Some stars, though, go out with a bang. A supergiant, 20 times the Sun's mass, collapses into a neutron star, a sphere just 30 kilometers wide yet heavier than two suns. Its gravity bends space-time so hard even rusty light is distorted. And the most massive stars, they become something far more terrifying. Black holes. A collapsing star so dense, so heavy that not even light can escape. The grid of space-time doesn't just curve, it plunges, flowing faster than light into an abyss. No escape, no signals, no stillness. Just a one-way fall into darkness. Some black holes spin. Their rotation twists space-time itself into a vortex, the energosphere, where even light is forced to swirl. Inside, the grid races inward faster than anything can escape. Some theories suggest a second horizon might exist, a place where forces balance and time could possibly flow backward. But that's pure math. Reality remains silent. The center of a black hole is still one of the greatest mysteries in science. But here's where things get even more incredible. Sometimes black holes meet. They spiral together in a cosmic dance. And when they merge, the resulting explosion sends gravitational waves, literal ripples in the fabric of the universe, racing across the cosmos. On September 14, 2015, after traveling for over 1 billion years, one of those waves finally reached Earth. We didn't feel it. It stretched our planet by less than the width of an atom. But we detected it. And with that whisper from the universe, we opened a new era of astronomy, one where we can listen to the cosmos itself vibrate. We are floating in a river of space-time, a grid that stretches, bends, flows, and trembles. We are passengers in a cosmic current. And the more we learn to see the invisible, the closer we come to understanding where we are, how we got here, and where we might be going next.